Example 3. One-sided limits. So recall from when we studied limits in Chapter 2 that one-sided limits can actually approach infinity, because one-sided limits describe a behavior of a function and not an actual limit that the graph approaches. So one-sided limits tell us more of a behavior, where if I was just looking for the actual limit, you could never get infinity. So with that said, let's look at the limit as x approaches 0 from the right of sine of x divided by x squared. What really helps me is to go ahead and draw the graph. So if we draw the graph out of sine of x divided by x squared, you get something that looks like this. And so this is the graph of f of x equals sine of x divided by x squared. Now notice, if we approach it from the right, so if we take 0 from the right, you'll notice that we start to approach infinity, and as we approach it from the left, you'll notice that we get negative infinity. That's how you determine it graphically, but we're going to determine it algebraically. So if we try to solve this by doing a direct substitution, we're simply going to get sine of 0 over 0 squared, which just becomes 0 over 0, which is indeterminate. This really doesn't tell us anything. So by using L'Hopital's rule, we get that this is the limit as x approaches 0 from the right of cosine of x divided by 2x. And now applying direct substitution, you get cosine of 0 over 2 times 0, which becomes 1 over 0. So as we approach it from the right, so I'm going to put a little plus here, 0 from the right, we can see that our graph takes off going towards infinity. And because this is a behavior, we can write that the limit as x approaches 0 from the right equals infinity. In part B, we're going to look at the limit as we approach from the left. So the same way as part A, if we plug in 0, you get 0 over 0. Doesn't really tell us anything. So by using L'Hopital's rule, we get that this is the limit as x approaches 0 from the left of cosine of x over 2x. And then by using our direct substitution again, we get cosine of 0 over 2 times 0, which is 1 over 0 from the left. And by looking back at the graph, when we approach from the left, we go down towards negative infinity. So this is going to be negative infinity. On your own right now, I want you to try to determine the limit as x approaches 0 from the left and from the right of tan of x over x squared. So the first thing I recommend you do is look at the graph. However, before we look at the graph, we're going to try to solve this algebraically. So here we go. Let's start with the one from the left. So we get the limit as x approaches 0 from the left of tangent of x over x squared is going to be tangent of 0 over 0 squared. And we're going to get 0 over 0, again being an indeterminate form, does not tell us anything. So we're going to use L'Hopital's rule, and we get that this is the limit as x approaches 0 from the left of secant squared x over 2x, and this is going to be secant squared 0 over 2 times 0, which is going to be 1 over 0 from the left. That tells us a little bit. That tells us we're either going to go to infinity or negative infinity, but we need to really look at a graph just to make sure. I want to solve part B algebraically before we move on to the graph. We're going to get a very similar result if we go ahead and plug it in. So I'm just going to go ahead and take L'Hopital's rule right away. And you get the limit as x approaches 0 from the right of secant squared x over 2x. And by plugging that in, secant squared of 0 over 2 times 0, which gives us 1 over 0 from the right. Again, either being positive or negative infinity, we're not sure. Now, if we graph tangent of x over x squared, we get something that looks like this, which is kind of hard to tell, so I'm going to zoom in and change the window just a little bit. So as you can see, as we approach 0 from the right, the answer is going to be infinity. And as we approach it from the left, we're going to get negative infinity. So this one is equal to infinity, and part A was negative infinity.